Welcome back to doing random problems from linear algebra done right by Algebra. So my ability to focus on these problems while I'm doing random things is drastically decreased, probably because I've seen so many of these that my head started spinning. But let's try and get through as many as we can. So suppose that S1 through Sn are injective linear maps. And then this makes sense, so that the composition makes sense, meaning that probably the output of each map is a subset of the input of the next one. So the output of S2 is a subset of the input of S1. I'm not sure that this is injective, so the first thought when I saw this is probably induction. So what's your base case? A function by itself is an injective function by itself is definitely injective. And the recursive case is if you have, let's say, a chain of n injective functions that composed, that makes sense. If you add like another function in front of it, then it's still injective. So assume that this is injective already. The same bunch of stuff, U2 if and only if U1 is equal to U2. And I think you can pretty much say the same thing about putting an S0 in front of this mess. Because I think what will happen is like these two things are actually equal. So since S0 is injective, then the results. I meant the other way around. So let's assume that these two things are equal. And then, of course, we try to arrive at the contradiction where these two are not equal. So assuming that S1 composed all the way to Sn of U1 is not equal to S1 composed all the way to Sn of U2, let's assume that these two are not equal. But however, oh shoot, I screwed up. Sorry, let me just go back and resync this. Alright. Yeah, I guess this is a problem, is like improving some of these things, because I don't know if I recall all the solutions from my head, because I've been thinking about this for maybe 2 days or so. So it's been a lot of questions is streaming through my head. So if it's base case, I think works very well. S1 inductive case, I think what you want to show is, given that you have a set of compositions S1 through Sn, if this thing is injective, you want to show that S0, which is an injective map composed with S1 through Sn, is also injective. So I think the way to go here is to say, like, assume given that these two are equal, the only way for this to happen is U1 is equal to U2, right? So let's assume the contradiction that these two compositions acting on U1 and U2 are equal without U1 and U2 being equal. So we're going to assume U1 is not equal to U2, right? But then by a definition of injective, if those two are not equal, then so isn't these two, right? These two are the input to S0 respectively. And if S0, since S0 is injective, it has two different inputs. You're going to get two different outputs, which doesn't work because it contradicts the original assumption that you can have S0 having the same input on both sides, even though their outputs, the outputs are the same, even though the U1 and U2 are different. So that's impossible. That's the recursive, or I guess inductive case, inductive hypothesis being shown there. So question 12. Suppose V is finite dimensional and the linear transformation T is an element of linear transformations from V to W, and prove there exists a subspace U of V. Subspace U of V such that you will know T is 0, and then the range of T is just, I think this is just some gibberish. I mean, it's just by the definition of, well, actually, no, it's not. It's saying the only elements, so if you map from V to W, then the only elements that actually get mapped by this T are the elements in U. Everything else gets hidden away somewhere, and I'm not sure where. But just looking at this question a bit more, it also suggests that U does not share any elements with the null space of T. So maybe to draw this more accurately, what you would have is you have your V, you got your null space, and then you got your U hanging around here somewhere as well. Yeah. And then the null space maps to 0 vector, while the U maps to T of U, which contains a 0 vector. I think this is all perfectly sensible because, and here's the reason why you can do this. Let's say V is a finite dimensional with dimension n. Then construct the basis of the vector space V with V1 through Vn. So this is a standard, or not standard, this is just a basis of V. And then pick, let's say, the first element to be inside the null space of T, right? So T of V1 is equal to 0. And then everything else just maps to let's just say that it maps to something. It doesn't really matter what it is. Some element of W somewhere. Prove there exists such that. Because I'm not sure if there are enough elements in U for this, but I think what could happen is V has got to at least have one dimension, right? So it's got to have at least a basis of size 1. Then you can choose only one element from the basis. The null space of T instead then consists of all the elements except the last one, right? So it's a span, the null space is all the span of all the elements in the basis of V except the last element, and then let T of V and be W1, and then it just works like that, I think. Because if you look at the range of the linear transformation, this is the only thing that is allowed to participate in the span of the range, right? And then, so that's why it's just equal to T of U, because U is just the span of V, and so this just sort of works out. And then it has 0 intersection with the null space. So I think you want to do something like this. If you got kernel, construct, extend the basis to the rest of the vector space, and then the kernel maps to 0, but the rest of the vector space maps to something meaningful. Okay, so suppose T is a linear map from F4 to F2, such that you got such a null space, and prove that it's surjective. So here you want to use, and whenever you want to talk about surjectivity or injectivity or something like that, you want to look at the rank nullity theorem. It's surprisingly helpful in many of these cases. And here I think an answer is called the fundamental theorem of linear maps. So what you have here is rank of the or not rank, what's it called? You can call dimension of the null space of T plus dimension of the range of T it equals to the dimension of the input vector space, or a domain, I guess, which is the dimension of F4. This theorem is actually a bit strange and axillary to read the proof for it. Sometimes you have to be above the proof, above the details, and try to get the big picture before you even start reading the proof, because otherwise the proof is just going to bog you down with details. So here you want to observe that the null space is dimension 2 and is in fact spanned by, let's say, 5 minus 1. Oh, I probably want to do this more systematically, where I use, okay, minus 5, 1, 0, 0, and 0, 0, 7, minus 1, or minus 7 plus 1, where I use x2 and x4 as 1s, as the variables I want to parameterize around, and x1 and x3 as being dependent on x2, x4. So I got two free variables, x2 and x4, so I can construct it like this. So it's got two, the kernel or the null space is dimension 2, so the range is also forced to have dimension 2. So that means the range of T, which is supposed to be a subset of f of 2, also has dimension 2, which means the range of T is just f2, because you got the same dimension as the set that contains you, so you're the same. If you're not convinced by that, construct the standard bases of the range, which has two elements, two independent vectors, and they also span f2. So I've done that a couple of times already, so I'm not going to do that. So suppose you use a three-dimensional subspace of R8, and T is a linear map from R8 to R5, and prove that the null space of T is U. Probably once again you want to use the fundamental theorem of linear maps. This is just reflexive at this point. So the null space of T is U, which means that the dimension of the null space T is going to be 3. And then the dimension of the range you don't know yet. And then is equal to the dimension of the domain, which is your R8, I guess. So that gives you 5. So dimension of the range is 5. If the range has dimension 5, and it's also this has dimension 5, it's also in R5. So once again, it's got to be the entirety of R5. So that's fine. Prove that there does not exist a linear map from F5 to F2 whose whole space equals this. Whose null space equals that. So once again, you want to use the fundamental theorem of linear maps. There's so many questions in this section, which is literally just about the fundamental theorem of linear maps. So it's not really like you're doing different questions, it's more of the same. So once again, you want to parameterize the null space using your free variables, and among each chain of equalities you want to choose one variable. So x1, x2, x1 equals 3, x2 let's choose x2, x3, x4, x5, they're all equal, let's choose x5. These two are free variables, and all the other variables are being parameterized around it. So it's going to probably look like the span will probably look like this. I think I'm not sure if I am missing something interesting. Yeah. So null space, which is spanned by these two vectors here, because x2 and x5 are free to move around as scalars. The null space is spanned by these two vectors and therefore has dimension 2, which means that the range has dimension 3, which is not possible because it's supposed to map to f2. So the range is supposed to be contained, so something of dimension 3 is supposed to be contained in something of dimension 2, which is not possible. Okay, so suppose there exists a linear map on V whose null space and range are both finite dimensional. Prove that V is infinite dimensional. I think actually I made a mistake here because I'm kind of suspicious about this whole shenanigan. No, actually, I think I just did it wrong because it just all just says it's this, right? x3 is equal to x4 is equal to x5. The same here, right? It's not like in the matrix form where you gotta consider the minus signs and all of that. It's just saying x1 is equal to 3 times x2. That's it. So if your x1's coefficient is 3 and your x2's coefficient is 1, that's fine. And if you do multiples of that, that's also fine. These are all in the null space. Okay. So suppose there exists a linear map on V whose null space and range are both finite dimensional, and then want to prove V is finite dimensional. This one's I think not a difficult one. So once again, dimension of null space is T plus dimension of range of T. And since both these two quantities are finite, their sum is also finite, which is the dimension of V. So that's fine. Question 17. Suppose V and W are both finite dimensional. Prove there exists an injective linear map from V to W if and only if there exists if dimension V is less than equal to dimension W. Well, so first let's go the first forward direction. If there exists an injective linear map, then you can map from so if there exists an injective linear map, dimension V is less than dimension W. And once again, you want to use fundamental theorem of linear maps, you guessed it, fellas and ladies. I don't know who's watching this. Okay, so dimension V is equal to dimension of I'll probably be careful around here because it's already, my brain's already falling apart at this stage. So zero dimensional null space of T plus dimension of the kernel of T. And since the map is injective, this is the fact that people, the range of T. Some people sometimes forget this fact. If it's injective, then the null space is 0. Because otherwise, you got two sinc doubles mapped to 0, then you're not injective, right? So null space can only have one element in it. If you got more than 2 elements, your dimension is not 0. And then what you got here is just dimension of V is equal to range, right? Dimension of the range. And we know that this is less than or equal to the dimension of V because range of T is a subset of V. It could be a proper subset, it could be not, but it's less than or equal to dimension of W. So we know that this, which is equal to this, is less than or equal to dimension of W. And that makes a lot of sense because you got an injective map, and every element in U is represented by somebody in another set. So the other set is probably bigger or equal to yourself from a very standard, from a very intuitive sort of view. So let's say dimension of V is less than or equal to dimension of W. And a lot of these questions you just gotta construct bases or bases. I'm not sure what the plural of it is of these vector spaces. So let's construct. Let's give the dimension of V a name N and dimension W also a name M. And then construct basis of V, V1 through Vn, basis of W, W1 through Wm. And it is known that N is less than or equal to M. So what you could do is take every single vector and map it to its corresponding counterpart. So T of Vj equals to Wj for all j that is between 1 and n. This is perfectly sensible injective mapping for every element that could possibly occur in here, or as a linear combination can be mapped to here using this mapping of bases, which is, I think, perfectly reasonable. Maybe one more thing to say there, and the reason because if you have some arbitrary element which is constructed using, let's say, some arbitrary element in V which is constructed using some linear combination of vectors in the space, vector space V, then the linear combination can be broken up, right? And once it is broken up, it now becomes some scalars times linear transformations on the basis, elements of the basis itself. So as long as you define these values, tv1, tv2 through tvn, what those values should be, then you define t itself on the transformation over V. Which is quick running through this. And suppose V and W are both finite dimensional, where there exists a surjective. So I think something very crucial about this finite dimensional stuff is you can construct the basis, and then you can like do the mapping. Because otherwise, you're not guaranteed to have a basis which is reasonable if you have an infinitely many dimensional thing. In fact, most of the time you don't, I think, but I'm not sure. So let's see. Suppose you have dimension V is greater than dimension of W, and then dimension V is equal to N, dimension W is equal to M. As usual, you want to show that. Let's go this way because I already wrote it down. Let's go if this is true, then you can do a surjective map, which you easily can, because what you could do is construct. Well, I say easily, but I've done this so many times that it's become easy. It's probably not. Yeah, so you want to construct the basis of V and from the vectors V1 through Vn and the basis W V1 through Vm. And since N is greater than M, you can just cut the first M elements of V and map it like this, as usual. And that's your surjective map. But the other way around, so if you got a surjective linear map, you want to probably use, you guessed it, the fundamental theorem of linear maps. I've said it a lot of times. So dimension of V is going to be equal to null space of V plus dimensional range of V. So we know that the range is just equal to dimension of V, and there's an equal to dimension of W, because V, the transformation T from V to W is surjective, so it covers everything. The range covers everything in W. So then dimension of V is equal to dimension of null space just plus dimension of W. And just looking at this, like dimension of null space can be a negative number, so this is at least greater than equal to dimension of W. So that makes sense, because if we subtract it over here, then dimension of V subtract the potentially positive or zero numbers, then equal to this. So that's true. So it's just a reasonable thing in general.